The mice get some symptoms of Alzheimer's disease, but they don't get full-blown Alzheimer's disease. And of course, if you think about it, there are certain cognitive tests you might do on human patients that are going to be really tough to do on a mouse. Where are your car keys, for example? But we have our ways. But the problem is we don't know how to develop drugs very well using the mouse, and the mouse doesn't get true disease. So then the question is, well, what are we going to do about that? So we're back to the same old problem. Guys like me need sources of human brain cells to study. Tracy, we're back to you. but this time it's going to be easier. So we're having a little clinic down in the lab tomorrow. Are you willing to come by? Let us get out the drill, you know. Get on in there. Just, I promise to leave most of it. And give back what we don't need. But even if I could get Tracy to let us do that to her, I have another problem. I don't really know if she's going to get Alzheimer's disease. She's young still. We don't know what she's going to develop. And so how am I going to study those cells anyway? Now, I can get cells from people after they've died of the disease, but now I've got the problem of I've discovered the plane crash on the ground, and I'm trying to reconstruct what went on in the cockpit before the plane crashed, right? You know, were they looking at their laptops and forgot to pay attention to driving the plane? Or did they run out of gas or something else equally silly? So we're looking for the black box of Alzheimer's disease in a sense. And of course, the way we're trying to do that, and this is where it comes back to stem cells, is I don't think that we're going to treat Alzheimer's disease by putting fresh neurons in, new brain cells in, at least in the near term. But what I think we can do is that we can use these human embryonic stem cells to make true human brain cells in a dish instead of relying on live donors. And we have genetic engineering methods where we can alter the genes and give those cells the same genetic changes that cause Alzheimer's disease. And we hope to begin using that over the course of the next couple of years to start screening for drugs that change the behavior of these cells. Because for this disease, I think we're going to do better trying to develop drugs more quickly, for that matter. So that's a sort of non-cell therapy-based approach. Okay, final vignette here, and then I'll take questions. Lou Gehrig's disease, a very different sort of example where you might be able to use stem cells to do something helpful. What happens in Lou Gehrig's disease, you may remember, is that there are special neurons that connect the spinal cord to the muscles, the voluntary muscles. And those motor neurons, as they're called, start to die. And they keep dying progressively until the patients are paralyzed. They can't swallow, they can't breathe. And it's pretty inexorable. Occasionally, it will spontaneously stop. Stephen Hawking may be an example of that, not entirely clear. But usually it proceeds pretty much inexorably to death. And usually it's 1 to 4 years from diagnosis to death. So it's pretty rotten rapid course. The issue, again, from the standpoint of a person or family member or somebody who has one of these things, is that there is only one FDA-approved drug for Lou Gehrig's disease. And let me use slang here. It sucks. It gives a statistical benefit to people who take it. It will improve the lifespan by a few months, but it has side effects, and people don't actually notice that they feel better. So it's really not a very satisfactory treatment. Now, the problem, of course, is, you know, again, what might you do about a disorder like this? And there are a variety of ideas floating around, but most of the current ideas that are being worked on come from a series of experiments that were done in my lab and my neighbor's lab, Don Cleveland, up at the university, where what we did is we made so-called chimeric mice. Those of you who follow the politics know that Sam Brownback really hates chimeras. He calls them hybrids for reasons I don't understand. You know, a chimera is like in Greek mythology, the animal that was part human, the Minotaur was part bull, right? Brownback seems to think that we're like, you know, it's like hybrid corn or something. I don't quite know what his deal is. Anyway, you can make mice that are a mixture of cells that have genetic changes that cause Lou Gehrig's disease and cells that are normal. and we have little markers so we can look inside the mouse's spinal cord and see who's who. And what we learn by doing that is that even though it's the motor neurons that seem to be dying in the spinal cord in these mouse versions of Lou Gehrig's disease, with that caveat always, it's mice at this point, the cells in the neighborhood, so-called astrocytes and microglia, cells that provide some physiologic support and interaction, those cells may be at fault or are certainly major players in the development of the disorder. And if you can make them normal surrounding a mutant Lou Gehrig's neuron, that neuron behaves better. Now, this is very interesting. One is it's interesting from a theoretical standpoint. Turns out a lot of the diseases we deal with are what we would call non-autonomous, meaning that the cell that's misbehaving visibly is maybe not the cell that's at fault. Now, this makes good sense, right? If you think about tissue and organs, all your cells are touching other cells. They're interacting like crazy. They're having conversations. They're exchanging messages and signals. And of course, the classic example of this is juvenile diabetes, type 1 diabetes, which you may or may not know is an autoimmune disease. So it's not that there's something wrong with the beta cells in juvenile diabetes. It's that the immune system attacked them. So it's a classic example of a non-autonomous disease. And so we think something analogous is happening in the spinal cord in Lou Gehrig's disease, at least in this one mouse version of it. Now, the good news about that is, if you were to think about trying to replace the motor neurons by transplant, this is a terribly difficult task because these cells have to wire from the spinal cord out to the fingers and the diaphragm muscles and everything else. Very tough problem. On the other hand, the cells that we think may be primary players, these astrocytes, they're relatively small. And so you could imagine transplanting those guys. And so a project that we hope to begin starting up in the next 6 months or so, CIRM willing, and we've heard that they're probably going to fund it, is to use human embryonic stem cells to make the cells that will ultimately make the astrocytes, and to transplant those first into the spinal cords of rats who are going to get Lou Gehrig's disease. That's what we call preclinical development at this point. It's to do experiments in animals before we get anywhere near a human patient and be sure that A, doing this kind of transplant really works, not just once or twice, every day, large cohorts of animals, no side effects, no tumorigenesis, 100 things that have to be done right before you get anywhere near a human patient. And if everything goes right, we hope to get this into clinical trials in several years. Now, who knows? This is a tough business. You know, we're more likely to fail than not, but it's a shot on goal well worth taking. Simultaneously, we have colleagues who are trying to use systems like this for drug discovery. Lou Gehrig's astrocytes plus normal motor neurons made from stem cells in a dish. Look for drugs. So you can sort of see where this kind of technology can start to take you by beginning to engineer bits and pieces of human tissues and recapitulate some of the disease processes in dishes. We are hopeful. We can't guarantee, but we're hopeful that we can make some progress on diseases that thus far we've been unable to treat. So that's about 15 minutes. That was my time allotment. So why don't I take questions at this point? And yeah. Oh.